Okay, good morning, everybody. Welcome to virtual seminars for Precambrian geology. This week, we're excited to have Dr. Michael Brown from University of Maryland presenting on secular changes in metamorphism tracks the emergence and evolution of plate tectonics on Earth. So Andre will introduce Dr. Michael Brown for us soon. Next week, we're going to have Dr. Rob Rainbird from Geological Survey of Canada in Ottawa. He's going to present on a talk titled Old Mushrooms to Meteorite Impacts, Highlights from a Geologic Transect Along the Copper Mine River, Canadian Arctic. So that's next week. And we're coming up close to the end of the year. And I forgot again to warn everybody, especially for international participants, that we changed the time here in the States last week. So we're on Pacific Standard Time rather than Pacific Daylight Time again. So apologies for not giving the warning, but so adjust for an hour change until we change back next year. So we'll start with the 45-minute presentation. At the end, we'll transition to our discussion session, which people can ask their questions either by putting their hand up or putting it in the chat, and I can ask it for you. So with that, let's go ahead. Andre, please introduce our speaker.
Thank you. It's a pleasure to introduce Michael Brown. Michael comes originally from UK and graduated in University of Kiel with undergraduate and PhD, and then hold several positions in UK before he moved to US in 1990. And he's expert in metamorphic petrology and on interface with tectonics, and particularly relevant to this seminars in terms of trying to use metamorphic petrology to constrain when plate tectonics started. And on the top of being world expert in metamorphic petrology, Mike for 20 years was a chair of a department at the University of Maryland and really put it up front and brought it to top 10 or top 7 departments in geochemistry, which is quite amazing. So with this, I pass it to Mike. And if you can unmute yourself.
Sorry about the delay. Well, good morning, good afternoon, good evening, good night. Welcome, everybody. I assume that everything's working fine, Alex. Oh, you can hear me?
Yeah, all is well. You're good to go.
Okay, thank you. Well, like a lot of research these days, I didn't do all of the work, but I am the person giving the message this morning. But I do need to acknowledge that a lot of the work that I'm going to show you was not only done in collaboration with many others, but is largely unpublished, although it's almost all in review, if not actually accepted in press. So I'm sure you're all familiar with the two images on the screen. On the left, we have Venus, and on the right, we have Earth. So at present, Venus is a single lid tectonic mode with a deformable lithosphere. It shows evidence of plumes, drips, and subduction, for example, at Artemis Corona, shown in the southwest corner of that image. And it contrasts with Earth, which at present has a fragmented, rigid lithosphere with a network of plate boundaries, weak plate boundaries, and evidence of plumes, drips, and subduction. The point being here that evidence of subduction does not definitively identify plate tectonics. So although the converse is true, that plate tectonics requires some form of return of material to the mantle, normally thought to be by subduction on modern Earth, the identification of subduction in the ancient rock record does not necessarily identify plate tectonics. And that, I think, is an important distinction that we need to make if we're going to try and work out Earth's tectonic history. So the null hypothesis that I'm going to work with today is that Earth has always operated in a plate tectonic mode. The alternative hypothesis would be that plate tectonics evolved from a different tectonic mode, for example, a single squishy lid or a sluggish lid, or possibly even a stagnant lid, but that seems less likely today. And we test this null hypothesis using the crustal record of metamorphism. And generally, we're going to try and work back from what we know at the present to what is more uncertain in the past. So let me, first of all, try and outline what we can obtain from metamorphic rocks. We can think of these as flight recorders or black boxes that track the passage of a metamorphic rock through the crust during orogenesis. And so to fully characterize metamorphic rocks, we need a number of parameters: temperature, pressure. I use the thermobaric ratio, which is the ratio between the temperature and pressure at peak conditions. And we need to know the age at which those temperature and pressure conditions were frozen into the mineral assemblage. And if we can get that kind of information at multiple points during the passage of a metamorphic rock through an orogen, we can determine pressure, temperature, time paths, and ultimately we can determine rates of heating, cooling, burial, and exhumation. And while these last four items, rates of heating, cooling, burial, and exhumation, are important, we have much less data on those than we do on pressure and temperature, for example, and pressure, temperature, time information. So in this study, we use 567 localities. They range in age from Cenozoic to Archean. And the constraint on the number of localities is broadly the age that we can determine and link to metamorphic PT conditions. We have many more determinations of temperature and pressure than we do reliable geochronological information. And I simply show the localities here plotted on the modern Earth to give you some idea that we have a global distribution. So what do these data represent? Each datum represents a point, which we commonly refer to as the metamorphic peak, on a geotherm crossed during a dynamic evolution, either from lower to higher thermal gradient, so from top left to bottom right in the pressure temperature diagram on the right-hand side, or from higher to lower thermal gradient, so from bottom right to top left. And we refer to these in this particular diagram, which is a petrological diagram, as clockwise or counterclockwise pressure, temperature, time paths. So the particular points that are shown there represent what we believe to be the frozen peak pressure temperature condition. And it represents an instant in time for a dynamic evolution of a rock that's undergoing some kind of burial and exhumation process on some kind of timescale. And during that process of thickening and thinning, the thermal gradients in the crust change, becoming either warmer or cooler, depending upon whether the crust is being thinned or thickened. So the first attempt at putting together, my attempt at putting together a data set, this had been done before by particularly Grambling, but the data were not really robust enough to draw good conclusions. My first attempt to do this was for a presentation at Stanford in 2005, when Louis Liu retired from his position as professor at Stanford. It was a conference after AGU that year. And I put together this data set of 144 data, and I based the classification on rock type, and it, in general, followed the principle of the metamorphic fascist series that was introduced by Miyashiro in Journal of Petrology in 1961. So I divided metamorphism into three types based on rock type: granulite ultra-high temperature metamorphism at the high temperature, low pressure part of the diagram, equivalent to the low pressure fascist series or Andalusite selimonite type of Miyashiro; medium temperature eclogite high pressure granulite metamorphism in the middle part of the diagram, shown in gray, This is the part of PT space where we have plagioclase bearing and plagioclase free mafic rocks as a consequence of bulk composition. And then the top part of the diagram in black, high pressure, ultra high pressure metamorphism, equivalent to the high pressure fascist series or jadeite glaucophane type of Miyashiro. So you can see this classification based on the mineralogy, which gives us the rock type, forms three quite discrete groups, and it appears to be quite a reliable separation into these three different types. And it appears to be consistent with the original metamorphic fascist series classification of Miyashiro, which, as you can see from the purple box in the bottom left of the diagram, was restricted to much lower temperatures and in particular, much, much lower pressures. So now we have a data set of 567, and I've changed the way that I describe these three different types. I now use what I call the thermobaric ratio, which is the ratio between the temperature and pressure at peak metamorphism. And that's what's used on the left here. And I use these colors consistently. So blue represents low temperature pressure metamorphism. Orange represents intermediate temperature pressure metamorphism, and red represents high temperature pressure metamorphism, equivalent to the three classifications you saw on the previous slide. Low temperature pressure metamorphism is represented by the rock types blue schist, quartz eclogite, or coesite eclogite, respectively high pressure and ultra high pressure metamorphism. And they occur at thermobaric ratios that are generally below 375 degrees C per GPa. At the high temperature end in red, high TP metamorphism refers to upper amphibolite and granulite fascist rocks, including ultra high temperature metamorphism, in the TP range generally from 775 to 1500 degrees C per GPa. And then in between, we have what I call intermediate TP metamorphism, again, comprising high P granulites and medium to high temperature eclogites, this area of overlap between plagioclase bearing and plagioclase free rocks, in the range 375 to 775 degrees C per GPa. And we believe that these can be related to particular tectonic settings at Earth on present, or at least within the last 200 million years. Each TP type refers to a specific tectonic setting, and we make the inference that these record similar tectonic settings in the past. Maybe not absolutely identical, but similar. So low TP metamorphism in the last 200 million years seems to relate to subduction channels and accretionary margins and subducted passive continental margins. And it appears to mark sutures in origins that are older than 200 million years. Intermediate TP metamorphism is associated with mountain building, and it records crustal thickening in origins greater than 200 million years old. And high TP metamorphism occurs in orogenic hinterlands, back arcs and plateaus, associated with lithospheric extension in origins older than 200 million years. So back in the early 2000s, I published a paper in 2006 where I looked at secular change based on that original data set of 144 data. And I drew 4 conclusions that are shown here. So the data are now plotted as what I called gradient at the time, but as a reviewer pointed out subsequently, it's not really a gradient, it's a ratio between temperature and pressure. And so that's why we now refer to it as thermobaric ratio. And you can see here the old terminology. At the higher thermal gradients, granulite, ultra high temperature metamorphism, now high TP metamorphism. In the intermediate range, eclogite, high pressure granulite metamorphism, now intermediate TP metamorphism. And at the lower thermal gradients, high pressure metamorphism and ultra high pressure metamorphism, or low TP metamorphism. And I argued that this duality that we can see in the Proterozoic, and in particular in the Phanerozoic, reflects of metamorphic belts of different type, reflects a duality of thermal regimes, and that has been recorded in the crustal record since the Neo-Archean. So in the Neo-Archean, we have a transition where we start seeing a separation between these metamorphic types into dominantly granulite UHTM and eclogite HPGM. A duality of thermal regimes is the hallmark of modern plate tectonics. This is effectively the point that Miyashiro was making in 1961. And the duality of metamorphic belts, I argued, was the characteristic imprint of plate tectonics in the rock record. So the occurrence of both of these types in the Neo-Archean, I argued, marked the onset of a proterozoic plate tectonic regime. Not the same as the present plate tectonic regime, because at that time of the absence of high pressure and ultra high pressure metamorphism. We now know that there are a small number of examples of high pressure metamorphism in the Paleoproterozoic, and I'll come to that later in the talk. So the Proterozoic plate tectonic regime then, I argued, evolved during the Neoproterozoic into the modern plate tectonic regime, characterized by colder subduction, as chronicled by the high pressure, ultra high pressure metamorphism. There was at the time a contrary view, which still persists, and that is Bob Stern, who in an article in Geology noted that, quotes, blue schists and ultra high pressure terrains indicate subduction and exhumation of oceanic and continental crust, and the modern style of subduction tectonics began in Neoproterozoic time. So we already have a contrast between a potential evolution from a Proterozoic style of plate tectonics to a modern style of plate tectonics, or alternatively, the modern style of plate tectonics beginning towards the end of the Neoproterozoic. So it's been clear from the start that if we look at the temporality of metamorphism, it relates to the supercontinent cycle. And this histogram could equally well be a histogram of zircons, and it would give you broadly the same shape, so that the argument about preservation versus crustal growth might be favored on the preservation side, just based on the fact that metamorphic rocks are, almost by definition, those that are preserved during orogenesis. So this looks like a preservation distribution, and it relates clearly to the formation of supercontinents. What has been less clear for the last 15 years is whether my assertion that there's a spatial association between metamorphism and convergent plate margins is correct. So I argued that a close spatial association in the past between metamorphism and plate margins, but that was inferred rather than tested. And of course, to test it, we need to have paleogeographic reconstructions. Those we now have that are sufficiently good that we can address this problem, and we have recently done that. So we've looked at metamorphism and convergent plate boundaries to try and justify the argument that there's a relationship back through time. So to investigate this, we couple metamorphic localities with plate reconstructions back to the early Paleoproterozoic, 2.2 GA, and then we test several null hypotheses about metamorphism and plate boundaries. And what I show on the right are just two examples of 8 reconstructions for particular periods of time, 600 to 400 at the bottom and 2200 to 1600 at the top, just to give you two contrasting periods. And located on those are metamorphic localities that fall within that age span. And you can see where they plot relative to the outlines of the continents or cratons. So the first hypothesis we're going to look at is that there's no association between plate boundaries and metamorphism. So we use 150 kilometers from a trench as a cutoff for defining metamorphism that's related to a convergent plate boundary. And that's just based on an average of the width of contemporary arc systems from a paper by England. And when we do this, and you can see the stacked histogram on the right, the colors are the same as they're almost the same as they were previously. Blue is low TP, yellow is intermediate TP metamorphism, and red is high TP metamorphism. About 80% of these metamorphic localities occur within 150 kilometers of a plate boundary, and fewer than 20% lie away from plate margins and could be plausibly related to intraplate metamorphism. Thus, we reject this first null hypothesis. There is a relationship between plate boundaries and metamorphism. Hypothesis 2 is that there's no relationship between metamorphic type and distance from the inferred trench. And what you can see plotted on the right as a log normal distribution is the distance from the inferred trench for, at the top, high TP metamorphism, in the middle, intermediate TP metamorphism, and at the bottom, low TP metamorphism. You can see that high and low TP metamorphism are skewed, respectively further away from and closer to the margins. and that intermediate TP metamorphism lies between these two. The medians make that clear, with starting from the trench side, 15 kilometers, 45 kilometers, and 62 kilometers. And then considering orogenic contractions, those distributions are consistent with metamorphism in the orogenic hinterland, the subduction channel, and the intervening mountain belt, respectively. Thus, again, the null hypothesis is rejected. Hypothesis 3, no relationship between low and high TP metamorphism along plate boundaries. So what we show here is the last 200 million years, metamorphic localities for the last 200 million years. And I just want to look at 3 plate boundaries. First of all, the Cordillera of North America, where you can see we have mostly high TP metamorphism with a single low TP locality, which is associated with an accreted terrain. And then moving over to the other side of the map in the Western Pacific, we have mostly low TP metamorphism with high and low TP metamorphism co-located in Japan. They're tectonically juxtaposed, of course. And then the Tethyan system in the middle, to the right of the word Amasia, shows a long strike variation from low TP metamorphism in the Alpine chain to intermediate TP metamorphism to the eastern end of the Himalayas, with rare high TP metamorphism. So yes, there is a relationship between low and high TP metamorphism along plate boundaries, although it's not common. So we can again reject the null hypothesis. The fourth hypothesis we looked at was that there's no relationship between paleolatitude and type of metamorphism, and we can only really do this for the last 1 gigaannum. And this is shown here by paleolatitude versus type of metamorphism. And the distributions do not support a relationship between paleolatitude and TP type. So in this case, we do not reject the null hypothesis, we accept it. But it does mean that the hypothesis proposed a couple of years ago by Yan and Zhang, that exhumation of low TP metamorphic terrains was limited to low latitudes, is actually falsified. And just a few additional observations on this study, which is in review. Metamorphism is closely associated with plate boundaries back to at least 2.2 GA. So there's both a temporal relationship with the supercontinent cycle and a relationship between metamorphism and plate boundaries. Paleogeographic analysis reveals that paired metamorphic belts sensu mirashiro, that's to say the close spatial proximity of low and high TP metamorphism, are rare. Mid-proterozoic orogens spanning both Columbia and Rodinia, shown in the bottom 2 panels, were dominantly hot. And the style of orogenesis has evolved from hotter, reflecting efficient unroofing of high TP rocks in metamorphic hinterlands prior to the Cryogenian, to colder due to exhumation of low TP rocks in subduction channels since the Cryogenian. So coming back to secular change and now plotting the larger data set as thermobaric ratio versus age, and you can see there are now 5 blue dots that have appeared in the Proterozoic during the last 15 years. We can ask several questions about this kind of plot, and what I put at the top is the suggestion back in 2006 that we had some kind of Archean tectonic mode that transitioned in the Neo-Archean to a Proterozoic plate tectonics mode that transitioned in the Cryogenian to the modern plate tectonics mode, and we'll see whether that holds up. So obviously the first question we can ask is, does low TP metamorphism in the mid-Proterozoic imply that we've had a modern plate tectonic mode since the Paleoproterozoic? And the other thing that's become apparent, shown here by plotting move-in means of the 3 different types of metamorphism, is that there's a metamorphic high in the Mesoproterozoic. And so we can further ask the question, what is the cause of this metamorphic high in the Mesoproterozoic? So I think, based on what I've said so far, we can erect 3 hypotheses for the Proterozoic. The first would be that there's a single plate before the emergence of plate tectonics in the Neo-Proterozoic. This is the case that has been argued by Bob Stern for the last 16 years. The second would be that because we have these low TP metamorphic localities in the Proterozoic, that modern plate tectonics extends back to the early Paleoproterozoic. There's multiple references that could be used to support that statement. And then finally, the original hypothesis that I published in 2006, that there was a different style of plate tectonics before the Cryogenian, and before that, there was a different style of tectonics in the Archean and a transition in the Neo-Archean. So we looked at that with Bob Holder here, published in Nature 2 years ago. This was a statistical analysis of the data set we had at the time. And given secular change, we argued that it might be more appropriate to consider the range and distribution of thermobaric ratios through time and not worry about dividing them up into metamorphic types. And if we do that, if we look at a statistical analysis of all TP and we bin them by age as shown here, so older than 2.2, generally Proterozoic 2.2 to 1.4, then broadly Mesoproterozoic to Neoproterozoic, and then finally most of the Phanerozoic 0.85 to 0.2, and then the modern regime from the Jurassic. We see that the bimodal distribution becomes increasingly distinct through time. It becomes first apparent in the Paleoproterozoic and becomes more divergent with time, with both the low TP and high TP strands of this bimodal distribution becoming cooler with time. And it's clear that late Archean metamorphism is unimodal, which is not thought to be characteristic of plate tectonics. So we can go back to our three hypotheses: a single plate before the emergence of plate tectonics, inconsistent with the appearance and evolution of bimodality since the Paleoproterozoic. So I would reject that. Modern plate tectonics extends back to the early Paleoproterozoic, which seems to be inconsistent with the divergence and cooling of low TP and high TP modes, which show that Proterozoic plate tectonics differed from modern plate tectonics. So I would reject that, which means that the third possibility remains viable, because with the present data, we can't exclude the possibility that there was a different plate tectonic style in the Proterozoic compared with the modern regime. Again, we've done some additional statistical work treating the data set as a whole, and what I show here are two features. This is the data set plotted as a time series of thermobaric ratio against age. The red curve is a locally weighted scatter plot smoothing polynomial regression through the data, and that shows a number of features, starting at the older end on the right, high TP in the Archean, a drop in TP associated with the Paleoproterozoic, and the occurrence of several examples of low TP metamorphism at that time, a peak in the thermobaric ratio in the Mesoproterozoic, consistent with the moving mean of high TP metamorphism, and a dramatic two-stage drop in TP associated with the appearance of blue schists and ultra-high pressure metamorphism. The horizontal gray bars that you see are means between the green and purple lines, which represent the outcome of sequential analysis by cumulative sum, which confirms statistically significant steps in the time series in the Paleoproterozoic, a drop and then a rise, and in the late Neoproterozoic, and particularly the Cambrian, with a couple of stops and a couple of rises. So this suggests that we indeed do have a tripartite division into an early regime, a transition to a Proterozoic kind of regime, and a transition to a modern regime. We recently confirmed that by redoing the statistical analysis using a different method and looking again at secular change and comparing that with state shifts in temperature, pressure, and thermobaric ratio. So what I've shown here on in the center part of the slide are simply plots of the 567 data for temperature, pressure, and thermobaric ratio. And then there's a linear fit at 95% confidence through the data, showing that broadly secular change is that temperature declines with time, pressure increases with time as the lithosphere becomes stiffer, and consequently thermobaric ratio also declines with time. And then we looked for abrupt shifts in the time series using a different technique this time, conjugate partitioned recursion. And this identifies change points, and those are shown on the right as changes in the mean at 95% confidence. You can see that there's changes in either the Cambrian or early Paleozoic, let's say, or the Paleoproterozoic. So there's a change in temperature in the Cambrian, there's a change in the pressure in the Paleoproterozoic and in the Cambrian, and there's consequently a change in the thermobaric ratio in the Paleoproterozoic and a significant drop and rise in the Cambro-Ordovician. Additionally, this time we've tried looking at cooling rate. Now, there are several issues with looking at cooling rate. One is that there are many less data, which is a little problematic. And the other is that the methodology involves two ways of determining the cooling rate, either using geochronology, which is shown as circles in the plot in the center of the slide, or using diffusion chronometry, which is shown as triangles in the center row of the slide, column of the slide, sorry. And then the top panel, you can see them by metamorphic type. We also show both exponential and quadratic fits to those data. And the one thing that's clear is that there's at least an order of magnitude difference between the cooling rate determined by diffusion chronometry and the cooling rate determined by geochronology. And what this means, of course, is that we can't combine the data sets, which is what people have done in the past, because they clearly are recording different elements of the process. And so we have to treat them separately. And we've done that on, the overall conclusion, of course, from the middle panel is that cooling rates increase with decreasing age, something that's been known for 20 years. So on the right, again, we use conjugate partitioned recursion to identify change points at 95% confidence. And again, you can see that there's either a change in the Paleoproterozoic or in the Paleozoic. And then this time we also have tried to relate this to mantle potential temperature. And to do this, we were kindly provided by Jerome Gain with a data set of 168 consistent potential temperature measurements. And we've shown these as plots on the right with linear and quadratic fits in the top two panels, showing again that as with the temperature of metamorphism, the potential temperature of the mantle is declining with time to the present day, as we know. And then looking at this with conjugate partitioned recursion, and to avoid the problem that might be generated by having a very uneven distribution of data, particularly in the Neo-Archean and in the Paleoproterozoic, we've used pooled ages, and this gives a significant drop of about 130 degrees Celsius in the mid-Paleoproterozoic. So what are the implications of everything I've said to date? Well, a change point identifies a minimum age for a state shift. So it reflects crossing a threshold leading to a new stable state. So we identify state shifts in the Paleoproterozoic and in the Paleoproterozoic. So this is generally confirming the Paleoproterozoic and Cambrian steps identified by Brown et al. In 2020. And in fact, it's broadly similar to the tripartite division suggested that I suggested in 2006. So the first change likely relates to globally stable subduction leading to supercontinent breakup, supercraton breakup, the amalgamation of the lunar megacontinent by plate collisions, slab breakoff, and more efficient cooling of the mantle. These are processes that are consistent with the operation of plate tectonics since at least the early Proterozoic. However, the mid-Proterozoic has proven controversial. Was plate tectonics intermittent, as suggested by Silver and Ben? Did plate tectonics slow down, as suggested by Sobolev and Brown? Or did plate tectonics stop, as Bob Stern suggested at the beginning of the year in GSA Today? Now, there are a couple of other features about the mid-Proterozoic that I've partly mentioned. First of all, it records anomalously hot metamorphism. This is the period when we have dominantly a Northosite and Rapakivi sweet magmatism. And it also appears to have a distinctive style of orogenesis, as Spencer et al. Proposed in GRL earlier this year. So on the left, I show the lowest curve I showed you earlier, emphasizing the peak in metamorphic thermobaric ratio associated with the Mesoproterozoic. And then on the right in the upper diagram, I've plotted the occurrence of massive type anorthosites by number. And you can see they're predominantly limited to the Proterozoic. And then in the lower panel, I've plotted them by area, if you'll allow me to take area as a proxy for volume. And this shows that most of the volume of anorthosites was in fact emplaced in the Mesoproterozoic. And you'll find a similar distribution, perhaps slightly offset to the late Paleoproterozoic for the Rapakivi suite. So is a plate slowdown a possible explanation for those data? So in the mid-Proterozoic, passive margins are few but long-lived. In fact, up to 600 million years in age at 1,500 million years in time. And you can see this in the plot on the right from Bradley's Earth Science Reviews article in 2008, where he's plotted by what he calls natural divisions of geologic time, the distribution of passive margins. And it's clear that in the Mesoproterozoic, passive margins are more than twice the age of those in the Archean, early Paleoproterozoic, and subsequently down to the present day, where some, of course, are still operative. So since passive margins record the tempo of tectonic activity, the peak in lifespan at 1,500 million years suggests a plate tectonic slowdown. So the next thing we've done is to test the null hypothesis of no change in plate velocities. And we've done this, and it's in review, O'Neill et al. In review. We developed a method of calculating plate velocities from the passive margin record, and we benchmarked that against velocities for the Phanerozoic, where they're fairly well known, certainly back to the late Paleozoic anyway. And we extended this approach to the Proterozoic, providing the first quantitative constraints on Proterozoic plate velocities, which substantiated the slowdown. And I'm showing you on the right the results of the calculation that show that plate velocities drop dramatically down through to the Mesoproterozoic. Thus, we reject the null hypothesis. And then we went on to use mantle evolution models to calculate the consequences of this slowdown for mantle potential temperature, which of course is higher in the past, melt volume and density, which are both higher as a consequence of higher mantle potential temperature, and extrusive efficiency, where extrusive efficiency is the extruded melt in proportion to the total melt, and that is lower in the past. And I can show you the results. If I can get my arrow back. So I'm just going to show you the outcome of the last part of that. So in the top panel of figures, you can see the average crustal density shown in blue for Archean, Proterozoic, and Phanerozoic crust, lithosphere, and the distribution of melt emplaced through that lithosphere for the Archean, Proterozoic, and Phanerozoic shown in red. And what you can see is that a higher proportion of melt is emplaced at the moho or into the lower crust in the Proterozoic than in the Archean and then than in the Phanerozoic respectively. And what this means in the lower diagram is that we have a lower extrusive efficiency. That's to say we have less melt extruded earlier in Earth history. And what is shown there, plotted in red, it's plotted in blue, is an evolving crustal density profile and an evolving melt density profile ratioed against each other back through time, with melt density changing with time. And also shown in red is a constant density profile. It makes really very little difference to the outcome. And if you look at the polynomial fit, you can see that there are minima in the extrusive efficiency in the period from 800 to 1800, which you might want to call the boron billion, or you might not, and in the early Paleoproterozoic into the Neo-Archean. So in the mid-Proterozoic, when plate velocities were slowest, we have a higher proportion of melt in place at the moho and into the lower crust, which enabled anorthosite and Rapakivi suite magnetism and generated the high in metamorphic TP. Well, of course, the question that follows, if there was a plate slowdown, is what was the cause? And I think I'm going back here to the paper that I published with Sobolev in 2019, I'm going to argue there's a role for global glaciation in secular variation of plate tectonics. So we know that there were two periods of snowball Earth activity in the early Paleoproterozoic and in the Cryogenian, where grounded ice sheets reached sea level at all latitudes. These widespread surface erosion events produced a large volume of sediments in trenches, and these are a necessary requirement to enable plate tectonics to work efficiently. And we argued that the first of these was related to the development of plate tectonics globally, and the second of these was related to the ability to subduct continental crust to mantle depths. And it follows that the mid-proterozoic plate tectonic slowdown was most likely due to the reduced sediment volume in trenches during the well-known Proterozoic glacial gap. So implications again, the widespread occurrence of ultra-high pressure metamorphism after the Sturtian snowball glaciation marks the transition to modern plate tectonics. And the peaks in ultra-high pressure metamorphism that are shown here in the purpley color in the graph on the right may be related to glaciations that provide sediments to trenches and enable transport of lower continental plates to mantle depths. And there is a relationship, statistically valid relationship, between the glaciations that are shown in blue in the Paleozoic and the peaks in ultra-high pressure metamorphism, where ultra-high pressure metamorphism lags the glaciation by about 25 million years. So to finish with one last thought, we can ask the question, do subduction and plate tectonics have the same birthday? So prior to the transition to plate tectonics, from the Meso-Archean to the early Paleoproterozoic, subduction may have started multiple times, but may not have been stable anywhere before the Meso-Archean. So there's no problem if you want to argue from a regional study of a particular craton that you have some evidence for volcanic rocks that appear to have a subduction signature. That might be perfectly correct. By contrast, plate tectonics emerged once subduction had become stable globally as part of a network of plate boundaries. So no, subduction and plate tectonics do not have the same birthday. To demonstrate plate tectonics requires the evidence of plate margin activity, but also evidence of displacement between lithospheric plates, which in terms of early Earth history means between cratonic areas. Thank you very much.
All right, thank you, Michael. This is great. You've had a good bit of action in the chat already. So I'm gonna start approaching that by reading a couple comments. So then I read things so that the people watching the video later can be in tune. So earlier on, Bob Stern wanted to mention that he wrote, I have acknowledged that something like plate tectonics existed between about 1.8 and 1.2 GA, see Stern 2018. He mentioned something that was slide specific. So maybe Bob, you can unmute yourself to talk more directly about that, if you would like.
Yeah, it's got to do with the hypotheses. Hypothesis 4 is needed. That, you know, I don't think there's much doubt that something like plate tectonics existed about 1.8 to 2.1. It's the time between that and the Neoproterozoic that Michael wisely focused on towards the end of the talk. So hypothesis number 4 is needed, which is hypothesis number 1. Modern style plate tectonics started in the Neoproterozoic, plus there was an earlier episode at 1.8 to 2.1.
Yeah, I don't disagree with that. Maybe I should have had a full hypothesis, but I would, of course, have rejected it because there's still evidence that you have the bimodality through the rest of the Proterozoic, Bob. But as you know, I believe we're closer, and our differences are over details. You believe we're further apart, but I think we can good-naturedly keep the discussion going.
Yeah, this was a fantastic presentation. Anyway, it was a great presentation, and
well, thanks. Sorry, I didn't quite acknowledge that correctly, but I guess I was focusing on the Mesoproterozoic and your GSA Today article, really.
Okay, the next comment was from Francis McDonald. Apparent plate velocities for Mesoproterozoic from Laurentia are some of the fastest in the record from paleomagnetism. See work by Nick Swanson and Heisel.
Well, the only comment I'll make on that is that the compilation by Selmiller et al., published in Precambrian Research a couple of months ago, shows a drop in plate velocities in the Proterozoic based on paleomagnetic data. I'm obviously not an expert on paleomagnetism, and my impression over the years is that there's quite a lot of discussion about whether the rates reflect plate motions correctly or whether there are some issues. So I'm not qualified to get into that debate, but certainly the compilation by Selmiller et al., which appears to have come out of a conference which was attended by most of the people that are involved in this, and that created the data set on which it's based, would appear to be consistent with the modeling that we did. Of course, like everything, that may or may not stand the test of time.
Yeah, I'll just bring up that the highest quality data for the Mesoproterozoic suggests very fast rates for Laurentia. So the high quality data seems to be inconsistent. So I'm just very curious where your estimates come from with a passive margin, because that seems like a very difficult jump to relate Bradley's passive margin frequencies to anything to do with absolute plate motion. So it's just, I think that's an interesting idea, but I think that data needs to be dug into more. That hypothesis could be wrong.
Well, yes, of course. I mean, I'm not going to argue that any of this is going to stand the test of time. Yeah, let's leave it there.
Yep.
Okay, the next array of comments starts into talking about CO2 outgassing rates. Paul Hoffman starts, if plate velocities slowed, we might expect that CO2 outgassing rate would slow as well, resulting in colder climate. A colder mid-proterozoic climate can be rejected as this period lacks any evidence for non-alpine ice sheets anywhere for more than 1 billion years.
Was that the end of it, Alex?
Yeah, that was the end of it. Yeah.
Well, I wouldn't argue with Paul about whether or not that was correct. I guess I would say it depends how much. Doesn't it depend how much you slow it down as to whether or not you would get that evidence, or is the reduction in CO2 outgassing going to be sufficient regardless? Again, it's an area where I have no expertise, of course.
Okay. Francis McDonald came up with another comment after that. Sedimentation rates calculated from Cryogenian glacials are the lowest in the geological record. You see our work from Barton and Sadler suggesting reduced erosion, not increased erosion.
Yeah, and I'll just couple up that with the data we have, both a lot of work by Paul mapping out the grounding line of glacial deposits in Namibia show that they are tapering distally and they're thin. And so from the geological record we have, I would suggest we have no evidence for increased erosion and sedimentation, and all the evidence supports exactly the opposite hypothesis. So I was just wondering, Mike, what you think if this hypothesis about glacial erosion, particularly for the Cryogenian, if it's not supported by the geological record, what else could be causing this change in metamorphism?
I mean, how generalizable is the observation from Namibia? I mean, there's been a number of papers published in the relatively recently, the last 3 years, I think, that have argued that glaciation does produce a larger volume of sediment. So again, it's an area where I don't have the expertise. I have to rely on the literature.
Okay, we'll just look at Antarctica and look at erosion
where there are
rates there.
stratigraphic constraints like Western North America, South Australia, South China, Mongolia, Southern Africa, South America, and Northwestern Europe, where there are stratigraphic constraints,
Yep.
the depths of erosion from the Cryogenian glaciations are meters to tens of meters. And where they are more than that, up to a few hundred meters, they are invariably in troughs, in bedrock troughs,
Yeah.
presumably the sites of former ice streams. So the stratigraphic evidence rules out great depths of erosion, similar as they do, for example, the Laurentide ice sheet in the Quaternary. In 2.5 million years, the depths of erosion are tens of meters.
Well, this comes back again to the fact that I'm reliant on the literature where there are opposite views. I'm not saying that that means they're correct. I'm simply saying that
well, you need to read the primary literature.
Well, I'm referring to primary literature, just presumably papers that you don't agree with. But I mean, you would agree with.
Well, look, if you're relying on Brendan Keller, posits the absurd hypothesis that
that's one example.
that glacial erosion in the Cryogenian led to a sudden surge in sedimentation 95 million years later at the beginning of the Cambrian.
Yeah.
So how did those holes in the ground survive for 95 million years unfilled? This is completely non-physical.
Yeah, it was that was the other extreme. Yes, you're right. I accept that.
And for what it's worth, the half-time isotope data from Keller, which is mostly 500 MA, is all restricted to orogens and Gondwana. If you plot it spatially, there's nothing on Laurentia or places, other places they're associated with the Pan-African orogenes. So it's just a big convolution.
So what comment would you make about sedimentation, if any, during the Proterozoic? I mean, would appear, so far as I can see, that we might have had higher mountain belts in the Paleoproterozoic during certainly during the formation of Nuna, maybe not necessarily during the formation of the younger components of Columbia, probably lower topography associated with orogenesis in the Mesoproterozoic, and then of course higher topography associated with the creation of Gondwana, the Gondwanan megacontinent. So would you relate that, the possibility of higher sedimentation to those events? Or would you say there's no change in sedimentation through time?
Well, there is papers by Rob Rainbird where he argued that sediments derived from Greenville went across whole North America. So at least Greenville Mountains must have been high enough to allow rivers to extend to western margin of North America.
Yeah, the Greenville's interesting, of course. It doesn't have any UHP metamorphism. So I'm not sure exactly how it fits into the scheme of things. The Grenville is a bit of an oddity to me. It also produces
what about Palin's point that the development of glaucophane schist depends on the magnesium number of basalt? And if you go back in time when the magnesium numbers are higher, under the same high pressure conditions, you get green schist.
Yeah, of course. I mean, the first 4 pages of that article, or the first 95%, are perfectly correct because they're a calculation. But if you then go and look at the compilation of basalt compositions for the Archean and the Paleoproterozoic from Condi, you'll find that more than half of them have less than 11.4 weight percent MgO, which is the cutoff to generate blue amphibole, glaucophane. So in fact, there are plenty of rocks, more than half of the Archean mafic rock record, if it were subducted, would have produced blue schist.
Okay.
But there's nothing wrong with the argument. I would expect to find if we had high pressure rocks in the Archean, they could easily be high pressure green schist. That's perfectly okay. But we don't have it.
The fact that there are no salt deposits in the Archean doesn't mean that the Archean oceans were fresh water. And similarly, the fact that there are no early Archean carbonates doesn't mean, as Daly thought, that the Archean oceans were limeless. Obviously, there was as much carbonate being deposited as there were rocks being weathered, because that's where carbonate comes from alkalinity and cations from weathering.
Right, but how much rock was being weathered?
This is a problem of preservation. And it has to do with the different residence times of different rocks types in the geological record.
Yeah, there's definitely a problem of preservation. I mean, I'm not going to argue against that. But if you look at the recent compilation of orogens in Nature, Earth and Environment by Weller et al., I mean, the level of exhumation of, say, the Trans-Hudson orogen is slightly deeper than, for example, the Himalayan Tibet orogen, but it's not hugely so. I mean, and you know, I've had somebody ask me a question previously where they've said blue schists are all found at the top of mountains. They've been eroded away. The Sulu belt's at sea level. I mean, you know, there's plenty
The
of.
trouble is the Trans-Hudson origin is mostly underwater. There's only a very small part of it that's even exposed. Most of it's under Hudson Bay, and the
Okay.
Hudson Bay lowlands Paleozoic.
My point is that while I accept that there's a preservation issue, it doesn't follow that every single low temperature, high pressure rock up until the Neoproterozoic has been eroded, and that suddenly in the late Neoproterozoic, we have examples around the globe, well, mostly in the Northern Hemisphere, admittedly, but around the globe. I mean, why do we suddenly get a whole bunch of them?
Well, there are Paleoproterozoic ones, but there are just not very many of them that have been
They're
identified.
not ultra high pressure, they're high pressure. They're generally overprinted eclogites.
So there are a bunch of other people who have things who would like to chat with you, Mike. So maybe we can move on from that. So there's a couple more comments about CO2 here. Bob Stern said, abundant within plate magmatism during Mesoproterozoic single lit episode is likely to inject lots of CO2 into the atmosphere. And Jing Jun says something kind of relevant right next. The CO2 outgassing rate is poorly constrained in the Precambrian, so one could get as much CO2 as they wanted.
Sorry,
So
is that a question? I didn't catch the end of that.
no, I don't think either of them were questions. They were just comments about CO2 outgassing. Next is from Lyle Harris. The assertion made at the start of the talk of subduction on Venus is incorrect. The sense of curvature of Archimedes, the example given, is the opposite to that of arcs formed by subduction, i.e. the opposite to the pushing on a ping pong ball analogy so often used to explain why arcs form on a spherical Earth. It is the interior of Artemis that has moved southwards, hence the opposite direction of motion required to be consistent with subduction, from Harris and Bedard 2014.
Well, it's a question of interpretation. I mean, there's interpretations that argue for it to be subduction related to plume generation, you know, subduction. It's the lithosphere inclined downwards and going back into the mantle. So whether it's produced by the mechanism suggested by Guerrier et al., for example, compared with Harris and Bedard, is arguable.
Except that
there's more than one interpretation, which is fine.
Sure, but Taras doesn't include the the observations that we have from two different data sets, the radar and the gravity, that there's a large lateral displacement there towards the south of the not only the center of Artemis, but the terrain to the north of it. And so, that's just something to be certainly added, to trying to work out the geometry. But it's just that given that, I agree with Taras's ideas for a lot of incipient subduction, but it's just even if that started to be, a sort of a downwelling, there couldn't be continuation of subduction given this southward direction if that were at the same time. But of course, we've got no way really with the lack of eddy geochronology to know the relative timing of any onset like Taras gave, or the movements that we see. That was just peripheral to the discussion.
I mean, the point of the slide, of course, was to make the point that plate tectonics requires subduction, but subduction does not necessarily require plate tectonics. So anyway, that's as I say, there's more than one interpretation of Artemis Corona, and let's leave it at that.
Yeah, sure.
Okay, the next one is from, I'm going to try to say the name properly, Renaud Susi LaRoche, I hope that's correct. Says, great talk, thanks. When calculating secular changes in TP, PT, etc., based on literature data, what is the effect of sampling or research bias? For example, are there proportionally more studies on UHP rocks compared to intermediate PT rocks because the former is more extreme and more attractive for research. In brief, are the PT data available in the literature a truthful representation of the whole rock record? Does it make a difference? Should we care about it?
No, yes, and yes. Well, of course, petrologists are notoriously bad for picking attractive looking rocks to work on rather than representative suites of rocks to work on. As I said at the beginning, the constraint on the size of the data set is having a good age determination that can be related to the rock form in mineralogy in terms of calculating pressure and temperature. It's the whole data set is inevitably biased towards those researchers that have access to the kind of equipment that enables them to obtain the mineral compositions and particularly these days, the multi-mineral petrochronology that is necessary and linked to the PT conditions. So there's inevitably a bias in the data set towards where ages are available. It's biased by design towards moderate to higher temperatures to ensure equilibrium for the metamorphic mineral assemblage. It is not biased in terms of being selective about the literature, other than using quality criteria to make sure, in particular, the age is related to the rock form in mineralogy. But yes, it has to be biased. The data set is 567. It's not 500,000 as the zircon, or a million, or whatever the zircon data set is these days that is available, the UPP data set for zircon. So it's not area weighted. So yes, it's biased. And you have to take it as it is until we have sufficient data covering the globe with sufficient quality that we can do something about that. And I've always acknowledged that, by the way. I mean, it's inevitable. And of course, the cooling rate data that I referred to is, another problem, because the data set is a fifth of the size.
Okay, there were a few follow-up comments in there. Sally Pearson pointed out that overall sampling bias is a huge issue with the Cenozoic data points in particular. Nick Roberts said, I compiled titanium and zircon from metamorphic zircons from the literature. I found it really hard to get intermediate TP data. So yes, I can imagine there's a lot of undersampling of amphibolite facies gray gneiss, for example.
It's hostage to the samples that people have collected and worked on, and particularly those samples where they've combined geochronology with pressure temperature information.
The next question is from Jean Bedard, and usually, Jean, you'd like to ask your own questions. Are you still here?
Yeah, I'm here.
Would you like to ask it yourself, or should I go ahead and read it?
Yeah, it'll be easier. Great talk, Mike. Very few, 4 little things. You said Venus was one plate planet.
Yeah.
If Lakshmi Planum drifted 1,000 kilometers relative to the rest, how can it be one plate, right? That doesn't work.
Well, I would allow for internal deformation. If that's too much for you, then maybe it's got a component of sluggish lid to it. Yeah, that's okay. It's not a plate tectonic planet, though, in the sense of Earth, is it?
No, it's not a plate tectonic planet.
Right.
Okay. You use the passive margins to calculate the drift rates, and as Archean passive margins are thin, rare, and sparse, how can you use that to calculate a drift rate?
We wouldn't. As you can see, it goes off the chart towards the Archean end of the spectrum. It's reliable for the Proterozoic, and I only mentioned the Proterozoic.
No, okay. You postulated a low sediment input to trenches to explain low Mesoproterozoic drift rates. By the same token, as there was very little erosion of continents, whatever, in the Archean, that means very low sediment supply, which would mean slowdowns, and yet you postulated very rapid motions, which is completely the opposite.
No, I didn't postulate any motions to the Archean.
Oh, well, other people did.
That's possibly true.
Well, you were arguing for very high motions in the Archean based, I think, on paleomag data.
No, I didn't I refer to paleomag data for the Archean.
Well, I saw some plate velocities somewhere on one of your figures. I can't remember.
There was a calculation based on passive margins, which
So how do you
extended
use
back to the Archean, and maybe it shouldn't.
Oh, okay. Final point. You were talking about intrusive-extrusive ratios.
Yes.
I don't know of very few places in the world where you can actually quantify that in any meaningful way.
No, the quantification is all over the place. I accept that.
Yeah. And
I mean,
you know,
it was based on one of the better known studies, but that doesn't mean that it doesn't have a whole variety of numbers in the table in the paper.
yeah, well, the argument is that, you know, the MOHO density barrier, or whatever the density is appropriate for neutral buoyancy.
Yeah.
Sure, that's a good argument, but basalts erupt. They don't all get stuck at the MOHO.
No,
And they
but some of them must get stuck at the MOHO or in the lower crust in the mesoproterozoic if we're going to fractionate and produce an orthosite.
Well, I don't think the orthocytes are produced by fractionation anyway, but the point is that
whether they were produced by fractionation or melting of the lower crust, we still need a mechanism.
yes, there's no doubt a lot of magma gets trapped at the MOHO, but they also erupt. So, and they erupt either because they're overpressured or because they're exsolving CO2 or something like that. So I don't think that's a very robust line of argument, is the point I wanted to make.
Well, I mean, it's
Polite, eh?
it's not robust because there are a limited number of estimates and they vary within a wide range. Yes, that's correct.
Anyway, great talk.
All right, our next question is from Matt Jackson. In your database, there are no UHP rocks of continental protolith before 650 MA. All pre-650 MA low TP rocks are either oceanic UHP rocks or non-UHP continental rocks. What are the implications of the fact that the first appearance of continental UHP rocks occurred at 650 MA, much later than the first appearance of oceanic UHP rocks?
Now, granted, there aren't a lot of UHPs at all before 650, right? But
oh, hi, Matt. Yeah. All right. I just realized you were asking the question. Yeah. Well, if I wasn't going to get into more trouble for sedimentation after the Cryogenian, I would say that the ability to subduct continental crust on a lower plate to mantle depths from the late in the Cryogenian onwards is what enables us to get continental UHP rocks. Now, whether the argument about sedimentation after the Cryogenian snowball Earth is reliable or not, we do seem to be able to subduct continental lithosphere lower plates at that time, and there does seem to be a relationship between glaciation and UHP metamorphism through the Paleozoic. Whether those are correctly interpreted in terms of sedimentation enabling subduction is another matter.
so you could be subducting continental crust at 650 and after, not necessarily sediment. I mean, sediment ultimately derives from continental crust.
Yes, of course.
You get continental material into the mantle.
I mean, the point is that argument comes from the Andes, where if you work your way down the trench, you go to faster rates as you go further south that relate to the fact that there's more sediment in the trench. So it comes from early work done by Sobolev along the Andean margin, that you need to lubricate subduction to make subduction occur faster. Now, whether that's necessarily done by sediments as opposed to altered oceanic crust, one can argue about.
So exciting talk. I mean, you're pulling me out of mantle geochemistry into something very unfamiliar to me, but it's super exciting. Thank you.
I did have a quick look through your manuscript. Thanks. I'll get back to you at some point.
Okay, from there, we really only have a couple comments from Catherine Bethune, Mary Louise Hill saying, saying we need more Archean samples. So there's a scarcity of pellets in the Archean that may skew the data. Other than that, there's not a whole lot here. Nick Roberts directed a comment at Jean. So maybe that's for you, Jean. But if anybody has any other comments they'd like to step up and, or questions, step up, feel free to unmute yourself and start the discussion. Daryl, you have something to say?
Yeah, I want to make a comment about weathering, because I think the weathering rate would increase post-glaciation rather than on. And a lot of your results seem a delay of several million years. The highest rates of weathering are related to tropical humid climates. And if you have equatorial, subequatorial glaciers and they retreat, the first environments they're going to get subject to are going to be these tropical humid settings. So that might explain some of your sediment supply things. But otherwise, given that these tropical humid climates create the most weathering, the mesoproterozoic doesn't fit.
Well, it would fit, wouldn't it? Because it would mean the mesoproterozoic wouldn't have high weathering rates. Would it not?
No, there's a lot of tropical stuff there. It's weathering.
Yeah, but if it's got more muted topography.
I couldn't argue for a less muted or a higher muted topography at the moment, given what we know about ancient paleoslopes. There's just not enough data.
Yeah, okay. But no, we didn't intend to imply that there was high rates of sedimentation while the Earth was covered in ice, but that as the ice retreated, we would get the sedimentation. Now, if that is not a viable hypothesis, and if as the glaciers retreat, higher rates of weathering is a viable hypothesis, then that would produce the lubrication that we're arguing for. You're muted, Paul.
The high rates of weathering following glaciation are because glaciers erode mainly by abrasion, and they produce rock powder, which of course has very high surface area to volume. So that leads to the intense weathering, not necessarily large sediment volume, but large surface area.
All right. Well, not seeing any more people raring to jump into discussion here. So with that, maybe Michael, it's a great time to thank you so much for this. You generated a lot of good discussion at the end there, and you were able to do it within 90 minutes. so that was great. Thank you everybody for your participation and being here. Next week we'll hear from Rob Rainbird. But until then, everybody stay safe, and international people or people who don't observe the change of time for going back to standard time for us, please remember to adjust your schedules and for when we'll be showing the presentation. So again, thank you, Michael. This was great.
Okay, thanks.
Thanks, Michael. I love metamorphic rocks.
Okay.
I'm a Barovian Buchan guy.
Thanks all.
Bye.